In this video, we're going to learn about the difference between strong acids and weak acids. Now, recall from the General Chemistry 1 class that a strong acid is a strong electrolyte, and remember, an electrolyte is something that dissolves in water and conducts electricity. Presumably it is forming ions. And so a strong acid is essentially breaking down completely and making ions. And so we say it is always 100% or very close to that dissociated. Or another word for that is ionized. So, for example, something like hydrochloric acid is essentially 100% breaking down and forming the hydrogen ion and the chloride ion in water. So we identify it as a strong acid. However, a weak acid is a weak electrolyte, which means that it is only partially dissociated. So it's much less than 100. Some of the weak acids are only a few percent, if that, dissociated. Or if you prefer, ionized. Ionized just really essentially it is forming ions. So a classic example of a weak acid would be something like hydrofluoric acid. So hydrofluoric acid undergoes sort of partial dissociation. So it's an equilibrium. I didn't draw the proper equilibrium arrows, so I'm sorry. And it forms H plus and F minus. So the question is, how do you know whether an acid is strong or weak? Well, it turns out that there are 6 strong acids that you have to memorize. And we may have asked you to memorize these in the first semester, but anyway, these are the 6, and essentially you just have to know if you don't see one of these 6 strong acids, then it must be a weak acid. So let's go and pull up a new slide and take a look-see. So this is a handy-dandy table in the book. So our first strong acid we have to know is hydrochloric acid, or HCl. This is stomach acid, by the way. The second strong acid we have to know is hydrobromic acid, and the third strong acid we have to know is hydroiodic acid. And if you look at the periodic table, and these are all acids based on the halogen plus a hydrogen ion. Notice HF looks like it should fit the pattern, but HF is actually a weak acid. And if we look at the other 3, we've got nitric acid, so HNO3, we've got perchloric acid, HClO4, and we've got sulfuric acid, H2SO4. And sulfuric acid is actually an example of a diprotic acid. So what do we mean by a diprotic acid? Well, in the first semester we said that acids can be classified as monoprotic or diprotic, and that is telling us how many protons or how many hydrogen ions they are capable of forming. So HCl is monoprotic because it can form 1 proton, or it can give off, if you like, 1 hydrogen ion per molecule. Now, sulfuric acid is diprotic, and what that is telling us that it is capable of giving, and I'll write an arrow here. It's actually an equilibrium. It actually loses the 2 protons one after the other, but it's capable of forming 2 hydrogen ions for every sulfuric acid molecule. So this is an example of a diprotic acid. So 2 hydrogens per molecule. We also have triprotic acids that can form 3, and in general, when we've got lots of them, we call them polyprotic acids, where poly means many. We'll just say one more thing about weak acids, and we looked at hydrofluoric acid, and we said it is capable of partially breaking down and making hydrogen and fluoride ions. But an even better way of looking at it is that it reacts with the water molecules, and it donates a proton to water, so it forms that hydronium ion, and it also leaves behind F-. We call this the counter ion, if you like. And if this HF is the acid, which is a weak acid, how do you know it's weak? It's actually not one of the 6 strong. Then the F- on the other side must be the conjugate base. And we can see this constitutes one of those acid-base pairs. Now, one of the surprising things, I think, is that given that HF is a weak acid, that means that the reaction is not proceeding very much forwards, but it's very favorable backwards. What that means is that for weak acids, they actually have fairly strong conjugate bases. So although HF is not a very good acid, F- is quite a strong base. Now, if you contrast that with a strong acid like hydrochloric acid, what makes it strong is that it essentially completely breaks down. So we replace the equilibrium arrow, which I think I wrote accidentally before, with just a straight arrow. So I'm going to write 100% over here. So it is forming the hydronium ion, right? It's given up its proton to water, and it's forming its conjugate base, so this Cl minus. Now, because this is a strong acid, that essentially means that there is just a forward reaction. There is no back reaction. So this means this thing here, although it may technically be a base, it is not capable of accepting a proton at all from water, because otherwise it wouldn't be 100% breakdown. And so this is not a base at all. In fact, it is going to be completely neutral. And in general, any of these anions that are formed from these acids, these strong acids breaking down, like hydrobromic acid is strong, so it breaks down completely this way. Something like hydrochloric acid is strong. We already saw that. Nitric acid is strong. HNO3 completely breaks down. Well, because it is strong, the back reaction essentially does not occur. So these two ions over here, if it were in equilibrium, they would accept the proton and act like a base and go backwards. But because the backward reaction is not possible because they're strong acids, then essentially these things here must be completely neutral. So these anions that come from those strong acids are always going to be neutral.